We need to stop lying to ourselves. For the last 5 years, the Western automotive media has been treating the new era of electric performance with a mix of arrogance, denial, and outright condescension. They called them straight-line appliances. They said they lacked soul. They confidently declared that the laws of physics were absolute, that an extremely heavy electric vehicle could never master a complex curve, could never replicate the delicate mechanical camber heritage of a Porsche 911, or the razor-sharp dynamic pedigree of a BMW M car. They cited Colin Chapman's philosophy, simplify, then add lightness, as the ultimate gospel, claiming that a 2.5-ton battery on wheels would forever be a clumsy, understeering mess on a circuit. They were wrong. Dead wrong. What you are witnessing right now with the latest ground-up electric architectures is not just a product launch or a marginal evolution. It is a humiliating, paradigm-shifting ultimatum delivered directly to the doorstep of the entire global automotive establishment. Think about the sheer absurdity of this situation. Technology companies and aggressive new manufacturers with 0 years of motorsport history, absolutely no heritage, and no dusty trophy cabinets from the Nürburgring or Le Mans, are building suspension and stability ecosystems that make the German giants look like they are operating in the Stone Age. We are looking at a fundamental and a violent shift in cornering dynamics. Most critics, blinded by nostalgia, will dismiss this as software gimmicks, artificial feeling, or digital vaporware. But they are missing the entire point. The new era of camber and curve domination is not a distant dream. It is a flex. It is a terrifying demonstration of the underlying architecture that already exists in fully operational factories today. This video is not about straight-line speed. Any fool can build a fast electric motor. This video is about the industrial violence required to create a suspension geometry so advanced, so predictive, and so intelligently woven into the chassis that it has effectively rendered the traditional method of passive springs, physical anti-roll bars, and reactionary dampers completely and utterly obsolete. To understand why this specific technology has terrified the legacy automakers and sent their engineers scrambling, we must leave the sterile design studio and enter the brutal physics of vehicle dynamics. The single biggest bottleneck in making a car corner perfectly is the management of weight transfer and dynamic camber control. When a vehicle enters a corner at high speed, centrifugal force throws its mass to the outside. If you build a traditional suspension focused on daily comfort, the car rolls heavily. The tire loses its optimal contact patch. The camber angle goes completely positive, and you understeer helplessly into a barrier. If, on the other hand, you make it bone-shakingly stiff for the track, the suspension cannot breathe. It skips over bumps, loses mechanical grip, and becomes a nervous, unpredictable nightmare on public roads. The old guard of the industry tried to solve this over the decades with complex hydraulic systems, active anti-roll bars, and variable rate springs. It was a brilliant idea for the 20th century, but it had a fatal, unavoidable flaw that kept chassis engineers awake at night: mechanical latency. In classical engineering, mechanics depend on a chain reaction of twisting metal, fluid pressure, and physical displacement. The chassis has to lean before the anti-roll bar can resist. The damper has to compress before the fluid restricts. You are forever stuck in a reactive catch-22. You either have a comfortable car that falls apart dynamically in a fast curve, or a harsh track car that shatters your spine on a pothole. The new generation of engineers completely refuse to accept this compromise. They realize that no static, physical geometry on Earth could meet their requirements for extreme, race car levels of grip, whilst carrying luxury car mass. So, they decided to completely remove the mechanical middleman. They didn't use guys in oily overalls adjusting camber plates with spanners on a test track. They used artificial intelligence and big data through proprietary, incredibly complex deep learning simulation systems. They tested millions upon millions of load scenarios, damper responses, and dynamic camber behaviors in a virtual environment. The result is a digital chassis that does not blindly accept the tarmac as it is. It anticipates, recalculates, and adjusts millisecond by millisecond, altering the tire's contact patch and the suspension load before the rubber even physically strikes the imperfection. Now that we have the digital brain capable of calculating the perfect corner, we need hardware violent and robust enough to execute its commands without hesitation. In the microscopic world of cornering dynamics, the tire's contact patch and the system's reaction time are the only metrics that genuinely matter. While the European pioneers of engineering were hitting the absolute limits of analog mechanical control, the new wave of technology looked at traditional systems and said, "We can do better, and we can do it faster." They built active suspension clusters powered by massive 800-volt high-voltage architectures. This is not just a car part. It is a terrifying display of instantaneous hydraulic and electric power, acting on advanced magnetic actuators. It reads the curve ahead through LiDAR arrays, stereoscopic cameras, and road surface scanners, mapping the topography of the tarmac in real time. It then fires immense counterpressure into the specific corner's dampers with absolute, surgical precision. The adjustment speed is so brutal, happening in the space of a few milliseconds, that it physically prevents body roll from even beginning to form. It forces the chassis to remain perfectly flat, ensuring aerospace-grade structural and dynamic integrity under massive lateral G-forces. Let us look closely at the result of this industrial violence: the rear suspension assembly. The component that traditionally defined whether a car was planted or loose in a corner used to be a nightmare of mechanical complexity. It was full of control arms, rubber bushes, and failure points that required constant alignment and fine-tuning. A standard high-performance car relies on thick physical anti-roll bars, twisting under immense load. The new architecture, however, processes the exact camber angle and required stiffness entirely digitally. The mechanical reaction time dropped from clumsy tenths of a second to fractions of a single millisecond. This is the absolute definition of first principles engineering. While legacy brands are proudly issuing press releases about their continuous, marginal mechanical improvements, the new generation has quietly achieved a quantum leap in mechanical grip. If the vehicle's AI detects a sudden change in the surface camber mid-corner, the system instantaneously alters the damper pressure and wheel angle to compensate, before the human driver even physically perceives the lateral G-force shifting. The profound innovation does not stop at reading the tarmac and adjusting dampers. The most radical, disruptive engineering decision in this new architecture is how they manage raw weight and traction mid-corner. In a normal combustion vehicle, the mechanical drivetrain, the prop shaft, the differentials, the gearbox is effectively dead weight. It is a heavy, rotating mass that inherently pushes the car wide off the tangent. Cell-to-body, or CTB technology, reverse this philosophy entirely. The energy storage is no longer treated as a heavy, compromised box bolted underneath the floor pan as an afterthought. It is integrated directly into the structural skeleton of the vehicle. The battery cells themselves bear the shear loads and twisting forces of cornering. But here is the true genius part: the lethal blow that separates modern digital control from the old world. Absolute, instantaneous torque vectoring. Engineers did something devastating to the legacy competition. By using independent, ultra-high-performance electric motors controlling individual wheels, they completely eliminated the need for heavy, reactive, and lossy mechanical limited slip differentials. When the vehicle aggressively enters a curve, the digital brain commands precise negative torque, regenerative braking, on the inside wheels, physically dragging the nose into the apex. Simultaneously, the outside wheels receive the exact, calculated explosion of positive power needed to rotate the car cleanly on its own vertical axis. This creates a virtual wheelbase effect. The car does not just steer with the front steering rack, it fundamentally steers with traction. This architectural layout creates a center of gravity incredibly low to the ground and a torsional chassis rigidity, that casually surpasses multi-million-pound carbon fiber hypercars. A four-door family saloon, engineered by technology companies, is now tangibly stiffer than dedicated Le Mans racing cars, boasting rigidity figures upwards of 50,000 Newton-meters per degree. This hyper-rigid platform is essential. It allows the active suspension to do its job perfectly, without any unpredictable torsion or flexing in the monocoque, ruining the geometry. We absolutely cannot talk about the chassis, the rigidity, and the camber precision without talking about the brutal, relentless violence this structure must contain. The core reason this architecture needed to be so impossibly rigid is because of the sheer kinetic force unleashed by the new generation of electric power plants. We're talking about motors spinning at over 27,200 RPM. This is not automotive territory anymore. This is jet turbine territory. When you throw well over 1,000 horsepower into a tight, demanding curve, distributing insane amounts of torque instantaneously to individual wheels, a traditional stamped and welded steel chassis would simply surrender. It would twist. It would flex violently. The mechanical spot welds would pop under the sheer, unadulterated stress of the lateral loads. But thanks to the integrated structural battery technology and the use of massive, monolithic, high-pressure rear castings, the new platform takes the maximum punishment without flinching a single millimeter. This is a holistic, closed-loop engineering victory. The advanced material science enables the unprecedented rigidity. The rigidity allows for the perfect suspension geometry and relentless camber control in the corners. And that flawless suspension allows the colossal, tire-shredding torque to actually reach the tarmac without instantly vaporizing the rubber. The tire does not shred, it grips, it digs in, and it propels the vehicle forward with a terrifying, calculated efficiency that leaves combustion cars in the dust. We need to conclude with a sobering reality check for the Western automotive world. The established European and American car industries are currently in a state of unmitigated panic. They are desperately lobbying governments for tariffs. They are trying to discredit foreign software and manufacturing techniques. They are clinging to the claim that the new physics of electric cornering are somehow illegitimate, synthetic, or devoid of character. They are frantically trying to change the rules of the game because they know, deep down in their boardrooms, that on the tarmac and in the curves, they can no longer win on a level playing field. But political tariffs cannot stop physics. You cannot legislate against superior grip, lateral G-force capabilities, and ruthless geometric efficiency. What this new generation of engineering has demonstrated with their absolute, uncompromising mastery of curve dynamics is that they have fundamentally solved the weight versus performance equation that plagued engineers for a century. They can build a car that is technically heavier, yet drastically more agile than a Porsche 911 GT3. They can build a chassis exponentially more intelligent than the old giants of Stuttgart and Munich. And crucially, they can manufacture it cheaper and faster, all at the exact same time. The era of good-enough mechanical engineering is dead. The era of relying exclusively on steel springs, passive control arms, and reactionary mechanical differentials is dead and buried. If you are not using artificial intelligence and big data to adjust instant dynamic suspension loads, and if you are not integrating structural batteries to achieve hypercar levels of rigidity through hypercasting, you are already obsolete. The tarmac has shifted beneath their feet. The die is cast. And for the legacy manufacturers who thought they owned the corners, the nightmare is just beginning.